So I'm going to talk today about some work I did with Paul Barston and Baylor, who I guess everyone knows, which is it's a problem that comes from number theory, but don't worry, there's randomness involved. Good, and also it ends up being basically just a problem about random hypergraphs. So I'm going to start with some motivation, and then the problem will quickly become one about looking for some large substructure in a particular inhomogeneous random hypergraph. Okay, so motivation. So how can you factorize a number quickly? For example, a big number like 8051. So can anyone see a nice way to factorize this number? So you could, of course, just divide by 2, 3, 5, so on. But that would take a while. Going to see a quick way to do it. So here's the solution. Add 7 squared. And observe that that's a square. So you immediately see that you get a factorization. Okay. So, okay, this is a nice trick. Unfortunately, in general, it takes a long time. It takes about the same time as just exhaustive search. So an important old idea, almost 100 years old, is instead of looking for one number that you can add, like 7 squared, look for a whole bunch of them. And okay, don't hope that each one is a square, but hope that you can find some subset of them, as in you can find some set of numbers whose product is a perfect square. And then take the product of these numbers, and you have 2 squares, which are congruent mod n, and this gives you some chance of finding. You don't know for sure that x plus y or x minus y is going to divide it, because it could just be trivial congruence, but at least it gives you a good candidate. And in practice, this is how people factorize numbers. Okay, so this very simple idea, and in some sense non-rigorous, is actually the basic idea that underlies modern factorization algorithms, including things like the number field sieve. Okay, so that's just some motivation. So okay, so it's interesting to try and find a collection of numbers whose product is a square. Okay. So a natural way to do it is to just pick the numbers. If you pick the numbers b, i randomly, well, the AIs you get are not themselves sort of uniform, but at least they're somewhat random. So one could try and understand what's going on. We can imagine that these numbers are random. And Pomerance asked, okay, what's the threshold for this property? So we're going to take a sequence of uniform, independent random numbers from 1 up to x. We're going to try and find a subset of them whose product is a square. We don't care how large a subset is. We just want the product to be a square. Okay. So the question is, how many random numbers do you need before you can find such a non-trivial subset? Okay. So more formally, let's take these numbers independently uniformly at random and define this t of x to be the stopping time, so the first time where you see a subset that's a perfect square. Is the problem clear? Okay. Okay, and the problem is actually determined this up to 1 particular 1 to the power. So we showed that you need about e to the root log x log log x. Okay. Okay, so let's. The upper bound is actually predates Pomerance, so let's see how it works. This is going to give us an idea of how to do the thing in general. So I'm going to write down this j of x that's going to be important to us. So what's j of x? It's the minimum over y of, so pi of y is number of primes up to y. This symbol I don't know the name of is a number of y smooth numbers. So that's numbers with no prime factor larger than y. Was it psi or something? No. All right, the number of numbers up to x with no prime factor larger than y. Okay. This is, in case anyone didn't know, I wasn't a number theorist, then that would give it away. Okay, you look at the minimize this ratio. and classical bounds on these numbers. So these two things have obviously been extensively studied by number theorists. Classical bounds tell us that this is roughly the order of magnitude of j of x. So this is the number that Pomerance proved. So it turns out that proving that j of x itself is an upper bound or 1 plus low 1 times j of x is not very difficult. So let's see what you do. So let's prove this upper bound, which is, in fact, the argument is due to Schrippel. So suppose we have more than j of x random numbers, and observe that each one is, because they're uniform, each one is y0 smooth, where y0 is the value that minimizes this. Right, minimize that min at y equals y0. Then each of these is y0 smooth with this probability independently, and by the definition of j of x, this is equal to pi of y0 over j of x, right? And you have slightly more than j of x of them, so with high probability you have more than pi of y0 that are y0 smooth. Okay, so far so easy. Okay, so it's just the same thing as I said. Now let's consider a matrix, a 0-1 matrix that encodes prime factors. So this matrix can be important, so let me show you a picture of it. Okay, so the columns are indexed by the primes, and the rows are indexed by the random numbers. And you put a 1, it's a 0-1 matrix, you put a 1 if and only if, not quite if the prime divides the number, because we care about squares, it's if the prime divides the number an odd number of times. Okay, if it divides twice, then that's good for you. Okay, and here's this y0, actually the prime, the pi of y0, and all of these numbers which are 0 to the right of this line, these are the y smooth 0 numbers. Okay, not quite, these are slightly more than that, but basically the same thing. So that you get this matrix S, which is the one that I defined in the previous slide. Okay, and so what's the claim? The claim is that S has more than pi of y0 rows, and it has pi of y0 columns, so by basic linear algebra, there must exist a subset of the rows that are linearly dependent, which is equivalent to a square. Okay, if you can sum a bunch of the rows and get 0 mod 2, that means you found a square. Okay, so that's the proof. Okay, so super easy. Okay, and Pomerance, the argument is the lower bound is harder. He managed to prove that at least this is roughly the right order of magnitude. Okay, and he conjectured that actually something much stronger is true, that this thing should exhibit a sharp threshold. Okay. So a big breakthrough was made a few years ago, maybe really 10 years ago. I think it was on the archive in 2007 or something, by Croot, Granville, Pemantle and Tetali, who proved the following thing. They determined t of x up to a small constant factor. Okay, so the upper bound is just a small constant better than this easy bound we just saw, and their lower bound is worse by a factor of pi over 4. So it's pretty close to showing a sharp threshold, but not quite. Okay, so I'm going to talk a little bit about how they proved this in the next slides. Okay, so this was a big breakthrough, and it's a difficult argument. Okay, so let's talk a bit about this proof. So in Pomerance's result, the lower bound was the hard part. Here, actually, the upper bound is the hard part. So for the upper bound, they use the same kind of approach, naturally. Oops, sorry, I'm behind. Yeah, so it's okay. I'll talk about a bit about the proof. But yes, so the upper bound was very difficult. The lower bound was relatively easy. It was just a first moment argument. So they conjectured that their upper bound was correct. And that's the result that I want to tell you how to do today. Okay, so they proved the upper bound already. We only need to prove the lower bound, but actually the method I'll tell you also reproves the upper bound as well. So I should thank Jonathan Lee, who, for those who don't know him, is a very clever young guy currently in Oxford, for pointing out a clever way of deducing this. I'll tell you that at the end of the talk. Okay, so how might you go about proving such a result? A very natural approach to people in this room is, let's just try and count something. Okay, if we can count the right thing, maybe we can prove something good, and this is what they do. So they counted, instead of just counting the y-smooth numbers, they counted numbers that are not quite y-smooth, but have a few extra relations between a bounded but arbitrarily large collection of numbers with a bounded number of prime factors lies to y0. So this is very difficult. Let me show you a picture. So it's things like this. Okay, so if you see 4 rows like this, you can add them together. You add up to 0 to the right of the line. That gives you 1 extra relation. Okay, so if you count the expected number, or so more, if you show that the number of these is sufficiently large, then you can add these to your column. Suppose here this is now smaller than pi of y0 as is. If you can add enough, then you can make this matrix S a bit bigger, and you can then use linear algebra again. Okay, so what they did, they counted these sort of bounded size even sub-hypergraphs in this matrix is a funny distribution, right? So for starters, the primes are changing, so the matrix is getting sparse. It's very sparse. It's getting sparser as you go to the right, but also there's annoying dependence. But the rows are independent, but there's annoying dependence between the columns. So when you see a number has a large prime factor, that changes the probability that a different prime is a prime factor in some slightly subtle way. So doing this required some clever number theory, some powerful tools from number theory. Also, they showed that the limit is, so they did some probability, they showed that some kind of limit exists, they did some analysis on the limit. So there's quite a lot in this apparently simple counting argument. On the other hand, to the lower bound, they just used the first moment method. So they counted the expected number of linear relations, again using these deep results from number theory, and showed that if t of x is just a little bit smaller, then that's small. So an obvious first approach to try and prove the upper bound is to say, well, maybe they just didn't count this cleverly enough. Maybe we can just do some better counting, use the first moment method, and prove the upper bound. And this does not work. So the first moment really does blow up. I don't know if it blows up exactly at this point, but it definitely blows up before you get to e to the minus gamma. Okay? So this is not obvious. In fact, we can only prove that it blows up by proving that's the threshold and then deducing it from that. So this is not obvious, but it's true. Yeah. So yeah, we wasted a few weeks trying to do this before. Before giving up. Luckily, Paul is extremely good at simulations, so he managed to convince us pretty well that it was going to blow up before we could prove it. So what do we do instead? So our first approach is dead. First moment blows up. Instead, let's follow a certain random process. Let's turn our random matrix into a random process. Let's follow it using martingales, which are going to turn out, so these things are going to turn out to be self-correcting. And it turns out the thing we're looking for, well, it's not exactly the 2 core, but it's contained in the 2 core. So we're looking for an even, so a sub-hypergraph of our, so you can think of this matrix as a hypergraph, of course. We're looking for a sub-hypergraph where all the degrees are even. That's certainly contained in the 2 core, because all the degrees are at least 2, because they're even. So if we can show that this thing does not have a 2 core, then we can show it doesn't have, we're talking about a lower bound, which will show you don't have a square. If we can destroy the 2 core, then we can destroy everything. Okay, so that's another very natural approach. Are there questions about that? Like that, at least that to be completely clear. So we're going to basically track the 2 core by removing leaves, basically. If we can destroy the 2 core, then we definitely don't have a sub-hypergraph in which all degrees are even. Okay, So here's our random process. It's not at all obvious what the correct random process to take is. Right? Though there's a reason, well, okay, there are various natural candidates, so here's the one that turns out to work. Okay, so here's our matrix again. So again, your 0 or matrix, you're 1 if the prime divides the random number an odd number of times. Okay, so let's call, instead of having these pi's everywhere, let's just call z the prime that we're on at the moment, and let's call z0 pi of y0. Okay, so starting from the right, we're going to reveal the columns starting from the right. Okay, so we're going to reveal this column. If we see that there's a single 1, then we know that we can't take that number. So if we take that number, there's no way to cancel out that prime. So we can delete the row. Now let's move z to the left, reveal the column, we saw nothing. This matrix is super sparse at the right, so this will happen quite a lot. Occasionally you see 2 1s, in which case you can't do anything, you have to leave it. Keep going, later here 1, you remove the row, keep going. Okay, now we saw 2 1s, but one of them is in a removed row, so we can remove the other one. Okay, so very natural. Yeah, so I made these slides for a talk to non-combinatorics people, so I apologize, this is a bit, if I'm patronizing you. All right, so there's 3, then one that gets destroyed, then there's 2, and then finally something interesting happens. Okay, so I want to look at this step. Okay, so we've built up all of these edges of our hypergraph, and then we add a 1 which happens to do the following. You remove it, that kills another 1, which then allows you, because we kill this one, we can now remove this one, which kills these guys, which allows us to remove these guys. Those avalanche, right? So very rarely you'll get these avalanches occur that cause a big change in a single step. And these are sort of the key to the process, understanding these avalanches. Okay, okay, and you carry on and then you go. Okay, so what are we going to track? Right? We've got a random process. We have to decide which variables we're going to track. The most obvious one to track is the number of rows, the rows that have survived up to step z. Right? And how large should m of z be? We need to guess the answer. And the answer turns out to be a bit funny. So let me spend a few minutes talking about this equation and why this is a natural thing to guess. Okay, so first, what are these things? So n, so we're slightly subcritical, so below the threshold. N is our number of rows, so that should appear, that's natural. This is the density of smooth numbers, so up to x. There's the probability that your qz, the zth prime, smooth. Okay. So the right-hand side is just the expected number of qz smooth numbers. Right? So you're the point z. Okay. What's the left-hand side? So m of z is the thing that you're tracking. So that's the number of active rows, times e to the minus something should be the number of rows that are completely 0 to the right. Now, okay, you have to make the hypergraph in the right way round, but the number of completely 0 rows is the same one way round as the number of isolated vertices in your hypergraph. So you have this hypergraph that you're tracking. This right-hand side tells you how many isolated vertices you have. This tells you how many vertices you have. So obviously, this thing should be the average degree of your hypergraph. Right? If the average degree of your hypergraph is a constant, and your hypergraph is random, then your number of isolated vertices should be e to the minus average degree times number of vertices. Okay? So that's where this comes from. This is incredibly natural. And it turns out that this exponential integral controls the average degree of the hypergraph. Okay? And we're going to show this is true all the way from the beginning, from the largest prime, all the way down past z0, a little bit further. So it turns out we only have to go, so there's this bottleneck, the that really the crucial phase of the process is close to this Z0. So remember, this is the matrix. This is this Z0. This is this point at which you minimize this guy. If you can go a little bit further, suddenly your life becomes much easier. And in fact, so it's important that we go this much further, because once you've gone e to the minus some large constant times root log Z0, then you can apply the Croot, Granville, Pemantle, Tetali first moment argument, and then it works with this extra information that your number of rows has gone down a little, just far enough. Okay, so it's important that we really go this far for some technical reason. Okay, yes, it's to do with the way in which this number of smooth numbers changes. So in order to make the right hand side, yeah. So I'll draw a picture. In fact, immediately. Here's the picture. It's going to tell you what's going on. So this is the same equation, except I've just rewritten things to make it look a bit easier. So this, right, so this j of x times this guy is n. I've divided both sides by z, and I'm plotting m of z divided by z. So suppose we're at point z, and then there's a certain number of guys we've got rid of, and there's m of z guys left. So the ratio of mz over z follows this very nice symmetric pattern. I didn't actually plot this. I just this is an artist's rendition of what the thing looks like. But it is very symmetric. So we prove that it's very symmetric. If you look at the right scaling, so the scaling on this is you go one step to the right, you multiply by e to the root log z0. Okay. So it's symmetric under if you take a log scale and normalize correctly, then this thing is very symmetric, and it starts off m of z is much smaller than z. It grows to some large constant which depends on epsilon, right? Where epsilon is how much space we have before the threshold, and as epsilon tends to 0, this alpha tends to infinity. So the proof breaks because this thing goes to infinity. And once this point is unbounded, once this ratio is unbounded, we lose control of our process. Okay, so it's very important in the middle of the process that this ratio is bounded at all times. Once it becomes unbounded, we lose control. And really, I mean, we know that that's actually what happens, right? So if you're a little large, if you're at this point plus epsilon, then really this thing goes to infinity and never comes down again. Okay. The thing gets stuck, and you really do have a 2-core. Okay. Okay. So this is a natural thing to guess. It has very nice behavior. It sort of gives you some understanding of the threshold. Okay. Any questions about this? Seem okay? Okay. Good. Right. So what we want to do is we want to control so we need to do sort of two things. We need to show this random hypergraph is sufficiently random-like, and we need to control the average degree of it. So what we're going to do is we're going to control the number of columns. So perhaps I'll do this again. Right, so I'll do a bigger version of this picture. I think, if I can manage to. Right, so suppose you've gone as far as Z, then there'll be some columns which have 2 1s in, and okay, I'll just draw the active ones, and some columns that have 3 in, and so on. Some columns 4, and so you can think of this as being a non-uniform hypergraph with these vertices and edges of different sizes, and let sk of z be the number of edges of size k at time z. Okay, which is just here, S2 of z is 2, and S3 of z is 1. Okay, so we want to show that the average degree is about this exponential integral, which turns out to follow if we can show that the probability that a certain large prime j has exactly k is an edge of size k is about a binomial distribution on mz of density 1 over j, which is roughly what you'd expect if everything was independent, and so it's not that this 1 over j is not the probability that this prime divides the number. That's the distribution. It's the probability if you assume that every larger prime does not, which is sort of natural because we're biasing we're in mz, we're in rows that haven't been destroyed, so it's much more likely that you have zeros to the right. If you ever have a 1 to the right, it's difficult for this guy to survive. Okay, so the distribution is not the original one, it's some funny biased subset, except the bias luckily is of a nice form, it's just conditioned on everything being 0 to the right. Okay, so that's what we want to show. Okay, and if you write it out, then this is what you expect to follow. So you expect the number of k edges at point z to be this funny function, I mean, not so complicated function of m of z over z. So just some things to point out. We're doing this is only going to be true near the critical point. Below, so critical point being z0, below that point, we can stop, we don't need to prove anything, we've already won. Above that point, life is a bit easier, and so we don't actually need this Titan approach. So we prove something a bit weaker at the beginning, and that's plenty. Okay, so this is the critical window of sort of you multiply z by a factor of e to the big O root log z. Another thing is the error term, which, so epsilon is small. This lambda, perhaps just forget for a second. Think of it as being a constant. It's important in the proof, but not right this second. This error term is a function of k. This is something I really want to emphasize as being relevant for all of you in other settings. It decreases at first, and then increases as a function of k, right? We're doing this for every k. So our bounds are, as k increases, first getting stronger and later on getting weaker. Now, there's a reason this is important. It's important that they get stronger, it will turn out, because we want these things to be self-correcting. And the change, the single step change in an SK, well, what matters? At a single step, you're going to destroy some of the k edges, so that's going to be proportional to SK. That gives you some self-correction, because the more you have, then the more you're going to kill. But there's also, you're going to create some from places like sk plus 1, sk plus 2. So it's important that the errors in those are not bigger than the errors in the guy that you're tracking, and for that reason it's important that this thing is getting smaller, this error. But this can't get smaller forever. Right? As k increases, you can't just keep getting stronger and stronger and stronger bounds. At some point it's going to be false. So luckily for us, at some point this k factorial takes over, because it's basically because these you expect to have, because our m of z over z is bounded, you only expect to have edges up to a certain size, some function of mz over z, and so above that size you don't expect to have many k edges, and therefore we can afford weaker bounds, essentially. And it turns out that this is quite delicate, but we can afford this k factorial, and so eventually these bounds just become trivial. So we follow this for every k up to the point where this k factorial is so huge that this just holds trivially. Okay? This is not a completely normal thing to do when following random processes. Normally, you reach some point and you're able to stop at some bounded value. But so in the triangle free process paper with Gonzalo and Simon, we didn't do this. We introduced this method where you just carry on until things become trivial, and this also helps here. So I want to advertise this idea that when you are following random processes, you can just let your error bounds grow until they hold trivially, and this does sometimes work. Okay. Yeah. So this lambda of z is just some funny constant, almost. So it's not constant. It varies with z, but it varies within some bounded range, which is sort of related to this picture. So you can think of it a bit like this constant. or in fact the inverse of this constant, more or less. That's not quite true, but it's some function of that constant. Okay, so if we can show that these SKs follow this nice family of functions, then then we can control the average degree, and then we can hope to prove the bound on the m of z number of rows follows the right function. Okay, have I still got half an hour? Is that right? Ah, good. So I can no, I have some more pictures, so this will take a little while. Okay, so if we're going to track these, so these are all the variables we're going to track, nothing else. Okay, so it's not super complicated. We need to control their single-step changes, both the expected change and the maximums change. We're going to use martingales, so these are the two things we need to track. So the key to doing this is to understanding these avalanches, these rare events when suddenly you see a single one, which allows you to delete a row, which then allows you to delete a bunch of other rows. So how large can these avalanches be? What's their distribution? And so on. And it's perhaps not surprising that we are going to use branching processes to do this. But doing so is a bit tricky, and really, so in order to do this, we have to modify the process. So we have to reveal less than we were revealing than I said earlier. Okay, so the process I told you before was okay for defining the random variables, but actually we have to be a bit more careful when defining the actual process we follow. So instead of revealing the positions of numbers, we're only going to reveal the number of numbers unless we have to. When do we have to? If there's a single one and we have to delete something. Okay. So once we know a column has a single one, then we reveal its position and the rest, and delete its row, reveal the rest of that row, and update the size of the edges in the other columns. So let's just see a picture of this. So this is the way we should think about this matrix in the middle of the process. So we've reached the zth prime. So this is its column. This m of z, sorry, I'm using capital M for the set of rows. And then there's a bunch of columns to the right. These are the columns we know have two ones in them, the edges of size 2. We don't know where they are. We just know that there's 2 and 3 and 4 and so on. So we know how many there are of each of these because we're tracking them. Okay, these are our SKs. S2 is the number of 2s, S3 is the number of 3s, and so on. Okay. So then in the step we reveal the number of 1s in column Z. In this case there are 3 of them. So we add Z to the set of 3s. S3 grows by 1. If nothing else changes, we move on. Life is easy. It's only interesting if there's a single 1, in which case we reveal this row, we remove this row, and then we reveal the ones that are the columns that have a 1 in this row. Okay? And so if there are 4, they become a 3, and if there are 2, they become a 1. But this 2 has become a 1, so now we know there's a single 1, so we know there's another row we can remove, so then we reveal where it is. Okay? And then we reveal a couple more. There's another 2 that's become a 1, so we reveal it, we remove it. Now there's a 3 that's become a 1. So again, this is for, not really for you guys, but pictures are fun, right? Then in that case, the third one gets removed, the 3 became a 1. Remove that guy, there's a 1, but he's removed already, and now we're done. Okay, so there's that's how we reveal the avalanche. Okay, so this is our branching process. So at each step of the process, we're going to follow this kind of branching process and see how large it is. And shock horror, we're in some random like hypergraph. You get exponential tails, and the expected number is 1 over the average degree, and everything behaves exactly as you expect it to. Proving this is not so simple, however. Main technical problem, I mean, number theory hasn't introduced itself yet, right? Number theory has to come in at some point. Here's where it comes. The rows and the columns are not independent of each other. Right? So you can't just reveal things and say, okay, great, next thing's independent, life is wonderful, got a Galton-Watson tree, whatever. We have these really kind of subtle dependencies which we have to deal with by some complicated number theory calculations using some powerful results about the distribution of smooth numbers proved by Hildebrand and Tenenbaum in the 80s, also used by Croot, Granville, Pemantle and Tetali. One of the big innovations of their paper, in fact, was to notice that you could use these powerful results in this problem. So this is not, it's not our idea to use this. This is those guys. Okay, so this takes really about half the paper trying to deal with all this. The paper's like 83 pages long, so this is quite a big chunk. Yeah. Okay, but then once you can do this, once you can control this branching process, then you can prove that these variables sk are self-correcting using this somewhat clever error bound that we use. Right, these error bounds are getting stronger and stronger and stronger at the beginning, up to some point at which life gets easier, at which case they blow up. Okay, so it's very important that we're doing this. Okay, meaning, what does self-correcting mean? Meaning if most of them are tracking, right, you have a bunch of sheep. If one of the sheep runs off, then it wants to come back with the others. Right? But if two of them start walking off, then you're dead. Right? You need to control all of them at the same time. But as long as the chance of someone being the first variable to drift off course is very small. Why is the probability very small? Because you can define a corresponding martingale and bound the probability that it's the first one to drift off path to drift. So yeah. So I don't know if it's, perhaps I'll draw this picture. So this is where you expect it to be. 0 means its relative error is 0, so it's following exactly where it's supposed to. So it's doing some kind of path, and then it crosses the line. We call it the line of death. Then what's the unlikely event? Well, let's look at the point 1/2. The line of death is point 1, so we call this a line of peril. What's the unlikely event? The unlikely event will cross the line of peril at some point, and instead of coming back, it went out. Because in this region, self-correction means that you've got this drift pulling it down the whole time. So its expected change is pulling it down the whole time. So in order to cross this from the line of peril, line of death, it's got to swim against the current for some non-trivial amount of time. Okay? And either this happens quickly, which is unlikely because martingales don't change quickly, or it happens slowly, in which case it fought against the drift for a really long time, and that's also unlikely. Right? So that means that the distance you've gone is much further. Okay, so this is yeah, and so this so I should give correct credit. So we discovered independently, but several years after, Bowman, Fries, and Lebetsky introduced this critical interval method. Okay, so yeah, you can define a martingale which starts here and ends here, and this is some unlikely event, and you just take a union bound over all such unlikely events. So this drift is contingent on all of the SKs, everything tracking so far. So if you are a particular SK, you're near your line of death, but everybody else is still within their line of death, then you get this drift downwards. Okay. So once we have control over all of these SKs, then we can deduce that m, the number of rows, really satisfies that equation. So what I say is that the SKs allow us to bound the average degree. So we know the average degree is what it's supposed to be. But why is the number of isolated vertices what it's supposed to be? Because our hypergraph looks kind of random. And this follows because the independent model is a close approximation to the truth. But I should say at this point we use a second moment argument. So our probability bounds are not very good. Okay, so this is sort of the weakest point of the whole proof in terms of probability bounds is here. Okay, are there questions about this sketch? Or about this picture or anything like this? I don't know how possible it is to really give you give details in a short amount of time. But anyway, okay. So if there are no questions, if there are questions, then yeah, please tell me to go back. Yeah. So because we control the SKs, we know our average degree is what it's supposed to be. So therefore, we can show our number of isolated vertices is really close to this. We know just by Chernoff that our number of isolated vertices is equal to this. If they're both equal to the number of isolated vertices, they're equal. Okay. Okay, so I already said this before, but let me just say it quickly again. We track m of z until it's very small. Very small means that you've gone past z0 until all the way to z is e to the minus some large constant root log z0 times z0. At which point m of z is a very small constant times z, which turns out to be exactly what you need in order to apply the first moment argument of Croot, Granville, Pemantle and Tetali. Okay, so in fact, we can just apply a result of those. It's not completely clear. I mean, so our proof does break down at this point. It's not completely clear that one couldn't do something cleverer and track it even further, but since we didn't need to, we didn't. And I said this earlier, since a square can only use active rows, because once a row's been deleted, we delete it because we can't use it. This implies that if we don't have a 2-core, we don't have any squares yet.
So you expect that below the threshold, the 2-core will always be empty?
Yeah, great question.
It could be that the 2-core is non-empty, but still you have no linear.
I think it's a fantastic question. I think it's an extremely, extremely good open problem, and I don't know what to guess about the answer. Is it true that the hitting time for having a square is the same as the hitting time for having a 2-core? Quite possibly, but yeah, I wouldn't like to conjecture it. But I think it's a really, really good question. Yeah. That our method, I did think about a bit, and our method definitely does not give. So you need to do something quite a bit stronger to do it. Yeah. Thanks. Any more? Yeah. So thank you for an excellent question. You've now intimidated everyone else, and they think they can only ask excellent questions. less good questions also welcome. Okay, for the upper bound. So sorry, I said we've now proved the theorem. We've proved the lower bound. Croot, Granville, Pemantle, Tetali proved the upper bound. But actually, so Jonathan Lee pointed out this nice fact. So a short calculation from our methods tells you that if you're very close to the threshold, when you get to z0, then you have a certain number of active rows, you have a certain number of columns you haven't looked at yet, and you have a certain number of columns that you know are non-zero, which is just the sum of the SKs. So you know what these numbers are, you know how many rows you have, you know how many columns you have. It turns out this matrix, it becomes very square. It's not quite square. I mean, if it ever went past being square, by linear algebra the whole thing would be false, but it gets very, very close. And so clever trick, just add a few more rows. So do our proof on almost all the rows. At this point, look at the final rows. Some of those numbers are smooth. That pushes you over the threshold, and by linear algebra, you've got a square. Okay? So actually, perhaps somewhat unsurprisingly, if you can understand the entire process from start to finish, you can actually prove both bounds, not just the lower bound. Okay. here's the main theorem again. So the threshold for a random set of independent uniform elements of 1 to x to contain a subset whose product is a perfect square is 1 plus 1, this e to the minus gamma. Sorry, gamma is this funny Euler-Mascheroni constant, which is very familiar to number theorists, perhaps less to us. It appears, apparently, I mean, according to Wikipedia, my knowledge of number theory, in lots of different places. There's weird ratios of different numbers that appear in number theory. Yeah, so it appears in our proof because, and in the proof of Granville and Tetali, because of this exponential integral. So the exponential integral has in it a constant term which has an e to the minus gamma in it. Right. And so, thanks.